This is example 2-15, ice floating in a cup. So we have a glass of water here, and then we stick an ice cube in it, and the question is how high does the water level rise inside of the cup? To start out, we'll say the ice cube is floating in the water, so we know that the weight of the ice, W, has to be equal to the buoyant force, FB. Now the weight of the water, that's just going to be the volume of the cube times the specific weight. Right? If we say that the cube length here is equal to A, then we could say that A cubed times gamma of ice is going to be the weight of the ice. And for our buoyant force, we know that's the weight of the water, because it's water is being displaced, times the volume that is being displaced. So maybe we can say the Vs here would be the submerged part of the ice cube, right? That'd be this part here, and then times gamma ice. All right, so that means we can solve this for our volume. So we know that the submerged volume, Vs, would just going to be gamma I. Oop, this is not an I over here, of course. Let's erase that real quick. This would be not ice, this would of course be water. W here. So then we were left with, if we divide by gamma water, right, we're at gamma ice over gamma water times A to the third. So this would be the volume of liquid that we're adding, right? We had nothing, but now we're adding this piece of real estate into it. So now what we can do is we can figure out what the overall volume is after we add the ice, right? So we can say, we'll call that volume N for our volume nu. So that would be our original volume plus our submerged volume, right? So our original volume was at a height of 10 millimeters, but then we added our Vs. So if we write some equations for that, right, then we of course know that V nu is going to be, we're going to have a diameter, so pi over 4 times d squared times the new height. That's what we're trying to find, right? So this would be the volume in this case. And then this is going to be equal to the original volume, which was pi over 4 times d squared, and we'll call it HO for H original. And then, of course, plus our Vs, which we figured out up here. Gamma I over gamma water A to the third power. Now let's look through here. The only thing that we don't know is our Hn. Right, D is given, that's the 50 millimeters. HO is given as the height here, 100 millimeters, and we're not given the densities, but we're given the densities, but obviously we can get those from here. Might as well just make that change in our next step, right? So then we can go and solve for Hn, which is here, right? We can say that we know that Hn is going to be all of this, so pi over 4 d squared times HO plus, and then we can straight away rewrite this here as not sigma. I'm not sure why I keep on writing sigmas instead of rhos. Rho ice times G over rho water times G, A to the third, and all of this, of course, divided by pi over 4 times d squared. All right. So we can cancel out those g's and rewrite this just a little bit. So we have Hn, right? We have pi over 4d squared in both these terms. So we'll just say that is HO plus, and then g's cancel. So rho I over rho water times a to the third and divided by pi over 4d squared. Now we can plug in all the values. So that would be 100 millimeters was the original water depth. And then we have the ice was 920 kilograms per cubic meter. Water is 1,000 kilograms per cubic meter. The cube length is 25 millimeters to the third power. And all of that divided by pi over 4 times, and the diameter is 50 millimeters squared. Now we don't need to switch away from millimeters because we want the result to be in millimeters, and there's nothing here that would require that. So we can say that will be equal to 100 millimeters plus what we have there, which is 7.32113 millimeters. So in total, we have a new depth of 107 millimeters. All right, so that would be the new depth that it was asked for, right, which is called H here. That's our HN. Now the question also is then, what will the water level H be when the ice cube completely melts? Right, so what happens if the ice melts? Well, to do that, we'll start out by figuring what the mass of H2O that we added, right? We know that the mass is going to be conserved, so we can say the mass is going to be the cube size, cube volume times density of ice, right? That's how much mass we put in when we added the ice cube. So now we can say what is the volume of water that we added, right, by adding this ice cube. So once it melts, what's the volume of water of that cube? So that would just be the mass divided by the density of water. Mass is up here, a to the third times rho ice, and then divided by rho water. Now, if we go back, this looks very familiar. If we look up here, this is exactly what we said the submerged volume would be, right? So that is exactly what we added here. So that means this is equal to Vs, right? Then we know that Hn is going to be 107 millimeters, right? Because we're adding the same volume. That means water level does not rise when the ice melts. Right? That's the answer to the second question. Right? So we saw that the water level rises by about 7 millimeters if we put an ice cube in there that has an edge length of 25 millimeters. And we also saw that the water level does not rise when the ice is fully melted.